Hi everybody, welcome back. So I don't know how exciting this video is going to be for all of you. It's probably going to be a small group of you who are going to be interested in this. But a while back I purchased this package of 100 BC549 transistors.
That's BR549.
And I bought them for like $2 and the shipping was like another dollar or two. And the question is, are they fake? And even if they are fake, are they fakes that are still good transistors, just rebranded as something that they're not? So I intend to find that out. So I thought I would test them. And I thought that would make an interesting video, how to go through and look at different parameters of a transistor. There's so many weird little symbols that you see, VCE, VCEO, VBE, ICE, all these things, HFE. What's all this stuff mean? I mean, I've gone through some of these and mentioned them in many other videos, but I thought maybe I'd go through some of them. And what I will also do is put a list that I will print up. I'll get all the ones I can. I'll type them up like on Notepad, and then I'll just print them on a sheet of paper and show them to you. And you can do a screen capture of them or something. And so you'll kind of have a better idea of what these things mean and what they are measurements of, of a transistor. So if that sounds interesting to you, stay tuned. And for the rest of you who will probably fall asleep of boredom, because not everybody, unless you're really into electronics, this stuff really doesn't mean a whole lot to you. For the rest of you, I have some really fun ones coming up here in the future. All right, let's get started. Now to test this, I'm going to use something you've never seen me use on this channel before. I've had this thing for about 2 years. I bought it. I thought it was going to be a great piece of test equipment. It turned out to be a real dog because it was very poorly built. It was kind of cheesy. It kind of sat on the shelf for a long time, and then one day I got it out and said, you know what? I'm going to find out what's wrong with it and see if I can fix it. And I was able to do that. So what this is a semiconductor or transistor analyzer. And originally it came with these little terminals where you just shove the transistor into the little terminals. And they were so cheesy and so cheap and so flimsy that the terminals would never make contact with anything. In addition, the selector switch didn't work properly. When you'd rotate it, it would kind of jump in and out. When I took this thing apart, as it turns out, when they assembled it in the factory, the circuit board is mounted inside here to the inside of this black bezel. And there was actually an extra screw that was wedged between the edge of the circuit board, like right about here, between the circuit board and this bezel. And it flexed the circuit board, which pulled the little tabs away from this switch, so those contacts weren't making contact properly. So when I removed that and cleaned it and reassembled it properly, and then I removed those cheesy terminals and just installed wires with some test hooks, now it works perfectly. So we're going to try it out and use it. Now I also have this little test board I just made real quick with this zero insertion force socket. It's really similar to what you see, on our little transistor tester things. And all I did was connected it there and put some binding posts so that I can just hook this on here. I figured that'll be easy. And this is also nice that I can put either transistors or integrated circuits or stuff in here. And I can use this for plus and minus rail, and I can jumper with my little breadboard jumpers from here to the little sockets if I want to wire something up and test it, make a little test jig. So I just made one of these up, and you can see how simple it is. So anyway, let me connect this up, and we'll do our first test. All right, for the first test, what we're going to do is we're going to look up the transistor here, the pinout, and you can see it goes collector, base, emitter. And so I have the collector, which is the red lead, going to the first pin here. I'm skipping the center pin, which is the base, and then I'm going to the emitter, which is the third pin. And I can probably hook this up and it won't matter, but you don't need this for this first test. So what we're going to check is VCBO. That is the voltage from the collector to the base. I'm sorry, from collector to emitter. We're going to check that first. Open circuit. So we're going to check VCEO. So you can see collector and emitter. With this test device, when you put it in VBR, which is V breakdown, in breakdown mode, it only uses these two pins to apply the voltage. And you have a 1000 volt range and a 200 volt range. So if you have one of these smaller transistors, you want to put it on the 200 volt range. If it's an NPN transistor and you turn it to this side, see NPN, the positive is going to be on the collector and the negative voltage, the negative return, will be on the emitter lead. Whereas when you're using it in PNP mode, it's the opposite. It will be a negative voltage will be on the collector lead and positive voltage on the emitter lead, if that makes sense. So it just flips the polarities around. And what we're looking at is forward voltage breakdown. So just like you look for VBE, which is what you use your little, voltmeter for, and it's usually 0.6 or 0.7 volts, something like that. This is a similar test, only you're checking from the collector to emitter with no voltage on the base, if that makes sense. So let's plug this in, and I'm going to turn this over to the 200 volt range. You don't want to touch this because it puts out a lot of voltage. And I'm going to hit the test button, and you can see it's about 72 volts is the breakdown voltage. And when we look at our parameter, this says it should be 30 volts. Now, these are going to exceed what it's rated in the book. This is what they guarantee is 30 volts. But because the breakdown voltage is higher than that, doesn't necessarily mean that these are fakes. Okay, so I'm going to take a few of these out. We're going to do a sample. I'm just going to do like 5 of them. That'll give us an idea. And if they all read the same, at least you know these are all pretty much the same transistor from that standpoint. But 73, so that other one was 71. Let's check this one. So you see they're reading over double of what the spec sheets are saying, but we're going to verify this. See, they're all the same. Very consistent. Okay. And that one's the same. All right. Now, just for reference, I have an actual from Mauser and DigiKey. I have a BC547, which is just the next one up. It's the same transistor. The only difference is it has a 45 volt breakdown instead of 30. Let's put this in and see what it does. And you can see it's almost double. It's 80 volts. So you can see they exceed what they're rated at. So that's good. So far, that's a good sign. Now for the next test, we're going to do VCB, which is collector to base voltage breakdown. And you can see, again, it's 30 volts. And what I've done is I've moved the green probe, which is the emitter probe, over to the base pin, which is the center pin. So we're now checking from from collector to base, VCB open circuit once again. And you can see it's really high, 150 volts. And again, if we go to our actual known good BC547, very similar. So it is possible that these are actually reading more like BC547s than BC549s, but we'll get to the next one. Should tell us a little more about it. All right, the next parameter we're going to look at is the breakdown voltage from the emitter to base. So VEB open circuit, once again. And for a 549, it should be 5 volts. And for a 547, it should be 6 volts. That's the maximum. And again, these are absolute maximum ratings. These can exceed this. So it can't be lower than that, but it is allowed to be higher than that. So I have this connected, and once again, you have to follow the book. It can be confusing. So if we want to look at the VEBO, emitter base, you want to connect the emitter lead to the base. So you can see here's the emitter lead connected to the base, the middle pin. And the collector pin, or you want to go to the emitter of the transistor. So the collector lead goes to the emitter, and that's how we have it. And if we press this, you can see it's about 11 volts. Now if we look at the BC547, it should be a little bit lower, but you can see it's 7 volts. It's a little bit lower, and you can see in the book it shows this one should be a little bit higher. So this one it should be around 5 volts. This should be around 6. Now these next parameters, the collector current, is the maximum current that you can put through the collector before it overloads and overheats. And you can dissipate 500 milliwatts of power. So if you, and even at 500 milliwatts, this is going to get really, really hot. So these are just things you don't want to exceed with your design ratings. These are actual parameters of the transistor. These are maximum design ratings, and you would have to test it to failure to see if these are at that. We don't want to do that. But that's what these are. IC is your collector current, the maximum collector current during operation. And this is the maximum power in heat, or in milliwatts. So it's a half a watt. Okay, now to check this next one, ICBO. So this is the collector cutoff current. And this is collector to base open circuit. And it cannot exceed 15 nanoamperes. Now it's going to be a lot lower than that. But the problem that we're going to run into is we're probably not going to be able to measure this. All we can do is measure if it's really bad. But if you look at the instruction manual, there is an ICEO, and it is a maximum of 2,000 microamps is all it can read. It puts about 27 volts across it, test voltage. And if you look here, the resolution is 1 microamp. So the smallest signal it can test is 1 microamp. And this thing reads 15 nanoamperes maximum, which is 0.015 microamp. So it's going to be way below the resolution of this meter. So if I put a transistor in here, I'm set to ICEO, and hit test, I'm going to get nothing. So you can see how that is. If I short the leads together, it'll give you an idea of your maximum reading. It's saying 1580, and that's limited by the wires and the maximum test voltage and so forth. But you can see it does work. It's just that it can't read low enough to actually read what this is. So that test can't be done with this little device, even though it says it can. Now on bigger, for instance, germanium transistors and things, you might be able to measure this and you'll see something on there because it's a lot higher. Okay, the next thing is HFE, which is your forward current gain. This is the most common thing. This and VBE are the two things you're going to see the most often. And right now we're looking at HFE, and on this transistor, it goes between 110 and 800, but you really have to look at this. There should be a letter after the BC549, and it should say what range that it is. So if it's an A model, it's anywhere from 110 to 220, B model and C model. Now the thing that people don't look at is they just look at this number and they're saying, oh, it should be this much. But the test parameters are really, really important. So when we're going to test this, we want to see for our forward current gain, you want to have a 5-volt test from collector to emitter, and you want your collector current, this is the most important thing, with 2 milliamps is what you're going to read this range here. As this changes, this will change. We're going to see that. So let me hook this all back up. So if you look here, this is your HFE tests. It'll go from here down to here. So you can have 10 microamps of base current, 1 milliamp, and 10 milliamps. And you can see, again, they're doing it at 2 milliamps. So the closest test we have is 1 milliamp. So this is probably going to read somewhere in this range, if not a little bit higher. It should read somewhere at 1 milliamp. It should read at the high end of this. So let's put this in. And this one, you don't have to hit the test button. You just plug it in. And you can see it's a 137. That's your forward current gain. And if I put my fingers on here and heat it up, it'll change a little bit. You can see it kind of, it's not doing too bad. Let's see. It's actually heating up with 1 milliamp. So this is a BC549C. So this is a C version. So this should be the high gain version. And you can see it's a little bit of an underachiever. And if we look at this one, BC547C, so this should also be in that range. It's even a little bit lower. Now, if I move this down to 10 microamps of base current, and again, this has to do with the amount of voltage. We're going to have to measure that too. Now it's up in that range. You can see 420 to 800. You can see it's reading 478. So it's not, this might be skewed because of the test voltage. Okay, so the next thing we're going to look at is VCE SAT, which is the voltage drop between collector and emitter with the transistor in saturation, meaning the transistor is fully turned on. Now here's the conditions, but I don't know if our tester uses these exact conditions. Now there is a 10 mA collector current and a 100 milliamp collector current, but what I don't know is if the base current is this, because it really doesn't specify it. So these numbers may not be perfect, but we'll take a look. So right now I have it set to an IC, or a collector current of 10 milliamps, and we can see we're in the VCE SAT test. I'll drop this in, and we're getting about 40 millivolts, and it's saying that typical at 10 milliamps is 90, and it might be a little bit lower than this just because our base current might be a little different. And let's just kind of compare some of these. All right, and let's look at one more. And they're all 40 millivolts. So let's look at this BC547, the known good one. It should be the same, and you can see it's 50 millivolts. So again, these are acting like true BC549s. I keep wanting to say BR549 junior samples. All right, some of you hee-haw aficionados may get that. Okay, now this next one, VBE saturation and VBE on. These ones are kind of tough to do on this tester because it does not have, it can't reproduce these conditions here. So I can check the VBE. So let's look at that. First thing we want to do is move this red lead to the base. So we want to have the base to emitter, and then we're going to remove the base lead again. And this is just going to check your VBE at 10 milliamps. Now again, you have to remember there is no collector current flowing because we have the collector disconnected. So if we do this, and you can see it's 770 millivolts with 10 milliamps. And that's actually pretty close, even without any collector current flowing. So, and again, if there was collector current, you would also be reading base emitter current. Might be, well, no, it wouldn't be. So that's pretty close. If I go to 100 milliamps, they're saying that it'll go up close to 900 millivolts. And it is 920 millivolts. So you can see it's pretty close, but that's not the exact test setup that they're using here, because they're also allowing for collector current to flow as well. But you can see that gives you a pretty close representation. Now VBE on, again, with a collector current of 10 milliamps and with 5 volts collector to emitter across there, it should be about somewhere no more than 720 millivolts. And at 2 milliamps of collector current, 660 is the typical. And again, that's going to be very similar to VBE saturated. So really, all this is showing is the representation of how the amount of current flowing from the base to emitter will change the amount of voltage drop you're going to have across that collector to emitter junction. Again, transistors, semiconductors in general, are a moving target. They're affected by temperature, they're affected by current, they're affected by the voltage across them. All those things can affect how the transistor works. But all we're caring about right now is that this stuff matches up, and it does. Now this little device is a kind of a manual way to plot how the transistor is functioning using those set points that they tell you in there in this previous page. But you can also use these charts. And if you take a look at this, does that look familiar to some of you? This is exactly the type of trace you're going to get when you're using a curve tracer. And really, a curve tracer does in a visual manner the same thing that this thing is doing by just plotting little set points on here. So what you're seeing in here is VCE, so your voltage from your collector to emitter. As you change your collector emitter voltage and you put a set or a fixed current on the base, it's going to show you at whatever voltage what your collector current's going to be. And you can see after this kind of turn on period, you see right there, and it's turning on. Once it turns all the way on, you can see the voltage, as we change the voltage between collector and emitter, it doesn't really care. The current is going to stay the same no matter what, because again, a transistor is a current controlled device. So really what you're saying here is your base current with a 50 microamp base current, you're going to see somewhere around 11 or 12 milliamps of collector current. See that? And you can see as you increase the base current, it also increases the collector current. So the collector current goes up with base current. That's why transistors are called current-controlled devices. But if you notice, once you get past this slope here, it flattens out pretty much. Now you can see it kind of starts to angle as you put real heavy current into the transistor. When it starts drawing heavy current, then the voltage will start to affect the collector current a little bit more. But generally, you know, when you're at lower signals, you don't see that. And so as a result, that's why some of these little test devices like this aren't always a really good indication of, you know, how a transistor is going to perform, because it can only check very, very low base current and very, very low collector current. It's very limited. This thing just has, you know, one little battery in it. It can't really deliver a whole lot of current. Even this just has 4 AA batteries. And it says when you use some of the heavier drive currents, you know, like when you're looking at the 2 amp, because this thing can actually put 2 amps of collector current. It'll actually drain the batteries very quickly, so they want you to use the external power supply. So this can actually work like at least a low-end curve tracer, you know, as far as testing the parameters, but only for smaller transistors. Big power transistors, 2 amps is nothing, because some big power transistors can go, you know, 20 amps or more. So that's what this curve tracer does. So if you're using the curve tracer, and you've seen me use those in previous videos, it's actually plotting this out. So they actually have a ramp signal, you know, like a stepped signal, where it's going to put a set current, and then it's on the base, and then it's going to drive drive the voltage up from 0 up to wherever you set it. And then it's going to plot out what your collector current does. So its collector current, you know, is this direction, and your voltage is this way, and each of these lines is a fixed base current that you're putting on it. And the curve tracer is producing all of those very, very precise and fixed test parameters. And it'll draw these little curves out. So that was a quick, well, not quick, this is probably a long video. I don't even know how long I've been doing this, but in my opinion, these are actual BC549s, and they're good transistors. And I don't know if they're actual Fairchilds, but maybe they are. The reason I was saying, when you see these really bright chrome colored leads and they're really thin and flimsy, those are typically not, you know, factory. You look at, for instance, these ones, they're just a little bit more dull. They're a little bit, the metal feels a little bit different, a little bit stiffer, better, bendier than these, but not bad. So these might be reproductions, but if they are, they're faithful reproductions and they work. And this will work in place of a BC549 or a BR549. All right, I had to say that again. So anyway, it's good news. I got a good deal on these ones. A lot of times you buy these transistors on eBay really cheap like this, and they end up being either the wrong transistor that's been rebranded, or they're flawed transistors. You'll go through and do these tests, and you'll see somewhere where one of these numbers is going to be way out to lunch. It's not going to track like a real version of that transistor works. So again, this is one way to test it, is with a tester like this. You can do some of these tests without this. So I'll show you a couple other things you can do. Okay, these can be purchased very inexpensively online, and they're called a transistor withstand voltage tester. And these can, once again, check the breakdown voltage of a transistor. Now, that's one of the only things it can do. And if I take one of these out, let's see here. And again, if I want to check the V collector-emitter, right? So VCE, or VCEO, which is your collector-emitter open circuit. I want to make sure I have this pin out correct. Yeah, collector-emitter. Yep. So there's the collector. The emitter goes, this is NPN, so the positive voltage goes on the collector, negative voltage on the emitter. If this were a PNP, you would swap the leads around. The positive voltage would go on the emitter, and the negative would go on the collector. Other way around. So let's turn this on. This is nice because I can set the maximum current that I'm testing it at, so I don't fry my transistor. This one just has a fixed current in there, and let's see what it is. So you can see the fixed current on that is 1 milliamp. See that? This one, I can go anywhere from 0.2 milliamps or 200 microamps all the way up to 3.8 milliamps. So that's really nice. I can, I can change that. So I'm going to back this way down, and I'm just going to set my voltage to, 470. I don't have to crank it up because, again, this transistor is only rated at 30 volts. So I just need a low voltage on there. I'll turn the power on. Hopefully you can see it. And if I hit start, 75 volts. And remember what we were seeing on that one was somewhere around 70 to 72 volts. So it's very close. And again, this also has to do with this. If I go up to closer to 1 milliamp like this had, it's still about the same. So this does the same thing as this for that. Now, you can do some things like you can do VCBO. So if you want to check the collector to base. So if we go to, there's the collector to the base, and I hit that, it's about the same, 150 volts, which was the same as what we were seeing with this. Remember, it was like 140, 150, somewhere around there, giving us the same readings, right? We can do the VBE, so base to emitter, VBEO, and VEBO, which is 5 volts. So I want to go backwards on that. So I want to go VEB. So this is like reverse voltage, emitter base. It's 11. See that? So you see how many of these things we can test just with this little cheap thing. So it works good. And then if you just want to check straight VBE, not saturated, but just straight VBE, well, you can take your meter and put it on diode check, and you can go from base to emitter. If I can hold this down here. There we go. And there you go, 700 millivolts, which was the same as we were seeing on that. And I could probably do that test here too. Since we're current limited, it won't matter. The voltage will just read correctly. And I don't know if this thing can go down low enough. I don't think it can read fractions of a volt. It can't. See that? It won't go that low. So you need your meter for that part. But you can see some of those tests you can actually do, and it'll give you an idea of how this all works. Now if I use this, sometimes if it sees a leakage voltage, it'll show ICEO. So let's see if this shows it. And there it is, ICEO, and you can see it's 1 microamp, or 0.01 microamp. It's super low. There's no collector to emitter open circuit leakage. And that's why this thing wasn't reading it, because it can't read that low. It was just reading 0 because it can only read in as little as 1 microamp, and this thing's 10 nanoamps, right? And what were they saying here? They were saying 15 nanoamps, and this was saying 10. So that's pretty cool. So it does show that. Now, what you'll find is, I think when you get a germanium transistor in there, it's a little bit different. Let me see if I have one handy. Okay, here is a germanium transistor, and I bet this meter will even be able to measure the ICEO on that. But let's hit this and test this one, see what it says. And look at that. Your ICEO for this is 51 microamps. Not not 10 nanoamps, but 51.4 microamps. So I think this would be able to measure it, because this can measure down to 1 microamp. And you can see this even shows ICE short, which is 0.1 microamps. So even your collector emitter shorted has these germanium transistors just inherently have higher leakage than a silicon transistor. It's just the way they work. So let's see. This was it emitter collector base? Let's see how it was. I failed to look. Emitter base collector. Okay, so let's go emitter. It's the same. It's reversed actually. Emitter, base, and collector. Let's put this in here. And let's go down to ICEO. And there it is, 78 microamps. See that? This one was reading 54. And it depends, again, on what voltage you're putting across it. This has lower volt. This is 6 volts test voltage. This thing was down to around 4. So some things are going to be a little different. So a little higher voltage here, a little higher leakage current you're going to see. HFE is very low on these. VCE SAT at 10 milliamps. It's about 80 millivolts. So that's it. And as I promised, here is a list of all the different transistor parameters. There's probably other ones beyond that, but this is it. Take a screen capture and check them out. All right, so I guess I can put all these transistors in this bag and put them in with my other ones. And we know that we have what we can call a good batch of BC549 NPN transistors. So I hope you learned a few things, and hope I didn't confuse you all too much. But until next time, I wish you all peace, joy, happiness, and good health in your lives. And I hope to see you again real soon with the next video. Got lots of cool things coming up, and we'll see you very soon. Take care, everybody. Bye-bye.